So to think through torque a little bit more, I thought it would be helpful to do an example that's much more connected to engineering as opposed to R cross P's and choices of origins and so on. And that's just a simple sort of torque speed example that you probably messed with some back in ModCon if you did the Lego Motor Lab, which I think you're still doing. Not sure that you still are. So the sort of setup here is that you've got a motor. The motor's hooked up to a wheel. And the motor has a characteristic which is called the torque speed curve. So I've drawn a sort of typical torque speed curve for an electric motor here. And the idea here is that an electric motor, if it's not spinning very fast, is capable of putting out a fair amount of torque. So if you think about a motor that's at stall and you're sort of holding the sort of crank of the motor will be pushing pretty hard against you. Whereas once the motor is spinning very quickly, it's actually not capable of putting out very much torque, and in fact there's a maximum speed that the motor reaches, at which point it can't actually make the wheel go any faster, and that's why the sort of torque drops as the speed goes up. Now different types of motors or engines have different torque speed curves, so if we were to draw the torque speed curve for a combustion engine or a steam engine or for a person on a bicycle, it would look different, but for an electric motor it typically looks something like this. And the reason I want to do this, I want to just think physically about what the fact that torque relates to angular momentum tells you about the behavior of this system. So let's think about this, and let's just start with basic principles that we have this wheel, and it's true that if I think about this wheel as an isolated system, so I'll draw the wheel, right? I'm going to cut that wheel out from the rest of the universe and ask what interactions cross that boundary. Well, there's one interaction that crosses the boundary, really, if I assume that gravity and there's a gravity and normal force offset each other. The wheel's not going anywhere, it's just spinning. So I just need to worry about the torque interactions that cross the boundary. There is a torque that is applied to the wheel due to the motor. So if I say that the torque is applying a wheel that's counterclockwise, I'll draw that like so. So I've got torque due to the motor that's being applied to the wheel. And that's the only external interaction, unless I were to choose to include gravity and the fact that the axle actually applies a normal force, but of course the normal force and gravity offset each other exactly in this case. So I could go ahead and write what the governing equations were for this system. It would be the case that sum of forces was equal to the time rate of change of linear momentum, which would be 0, because of course it's not going anywhere, it's not accelerating, the momentum of the system is not changing, and it's 0 because these two forces offset each other. Whereas the sum of torques would simply be whatever the torque of the motor was as a function of the current value of omega, and that has to be equal to the time rate of change of the angular momentum of the system. Well, the angular momentum of the system, since it's simply spinning, is simply the moment of inertia of the wheel times the angular velocity of the wheel. So I end up getting a sort of differential equation that describes the time evolution of the system that says the torque of the motor depends on what the current value of omega is, and that tells me in turn what the time rate of change of omega is. Now both of these are in the k-hat direction, so I could simplify matters and just write this as a scalar equation. So the torque of the motor as a function of omega is I times omega dot. Okay? So let's think about what's going to happen when I first turn this system on. What does this differential equation tell me the behavior is going to be? Well, if I think about plotting omega versus time, well, when the system is first turned off, when I haven't turned the motor on yet, omega is 0, right? So I start out with omega being 0. And then I turn the system on. Well, omega is 0 when I first turn the system on. Omega can't change instantaneously because omega tells me what the angular momentum is. Angular momentum can't change instantaneously. So initially, omega is going to be 0, and so I'm going to get a lot of torque, right? When I first connect the switch, a lot of current flows into the motor. That gives me a large magnetic force, which is turned into a magnetic torque that wants to turn that wheel. And so the torque initially is high. That's going to lead to a relatively large time derivative for omega. So initially omega is going to go up pretty fast. Okay? But now a little while later, omega has gone up a bit, right? And since omega has gone up a bit, the torque is a little bit lower, right? So now the rate of change of omega has dropped a little bit. Okay? Now, but still omega has kept on going up. Now maybe my value of omega is here, right? The torque is even lower, so the rate of change of omega is even lower. And this will keep on happening as omega speeds up and up and up. Eventually, the torque gets small enough that the rate of change of omega is quite small, and I sort of asymptotically approach this omega max. Right? So you can sort of see that as time goes on, I will eventually approach what that maximum value of omega is. Okay, so this is a case where the actual torque is a function of what the speed is, and since that it's a function of the speed, you end up having to solve this differential equation to figure out what the behavior of the system is. Now, obviously, in linearity, you're doing this type of differential equation. You could write this as a linear function. You could solve this differential equation analytically, and I encourage you to think about how to do that. But from a sort of conceptual perspective, the idea here is that torque tells you how fast the angular velocity or the angular momentum of the system is changing.